Hello everyone, and welcome to this second episode of our QWave series brought from QuIC. So today we will be talking about scaling quantum computing. It will be with VTT, so with Pekka Pursula and Sara Purshimal. And just to have a brief overview of QuIC, we are the European Quantum Industry Consortia, and we are a pan-European nonprofit whose mission is to help pushing the quantum technologies within Europe. And one of the tasks that we do beyond our usual expert group, working group work in the different verticals and streams, just like quantum computing and simulation, quantum sensing and metrology, and quantum communication, is more things like info session or even these webinar sessions. Today we will be talking, as I told you, about scaling quantum computing, and it's not only about that. We will also have a brief overview about the different projects, QTest and QPilot. So let me introduce our first speaker, that is Pekka Pursula. He's a prominent figure at VTT, and he's specialized in the development of quantum technology services. He has been an instrumental in design and implementing initiatives that support research and industry in adopting these quantum technologies. And today he will talk about the different quantum technology services at VTT, and then we will have an introduction about the QTest and QPilot projects and how these services are shaping the quantum landscape in Europe. So with that said, Pekka, the stage is yours.
Thank you, David, for the introduction and for the opportunity to join this QWave Webinar Series. So my name is Pekka Pursula. I'm a research manager at VTT on quantum technologies. And what I wanted to talk to you about is today that how VTT is providing quantum technology services and research and development for scaling up the quantum computers. So I'll start by giving you a introduction about VTT. So VTT, the Technical Research Center of Finland, is research and technology organization owned by the Finnish government. We are multidisciplinary. We have around 2,000 employees, and you can see that we are over 80 years old already. So we have been in this business of research and development for quite some time. Then if we go for quantum technology at VTT, VTT entered the quantum technology field in the 1990s, and the first kind of application we started to develop was quantum magnetometry. So that's SQUID magnetometers for medical imaging application, and that kind of from the very beginning, the role of VTT in this development was to stabilize the fabrication processes. So we were working closely together with the universities there who had kind of the basic research as their role, and then industries who were interested to take this technology in use in the application. And VTT was the partner there in between the university and the companies who actually stabilized the fabrication processes and matured the technology so that it could be taken into use by the industry. And this is the role of VTT overall. So we want to be kind of bridging the gap from basic research to the industrial application of new technologies. And nowadays we are building also a 50-qubit superconducting quantum computer at VTT together with the Finnish startup IQM. We have more than 50 researchers working only on quantum technologies and additional 200 experts on microelectronics, and those heavily support also the quantum technology research, because these both technology platforms are in the same clean room, and there's a lot of I would say joint actions from fabrication and development perspectives. So we have a in-house clean room, as mentioned, 2,600 square meters, where we have several technology platforms like integrated photonics and quantum technologies, especially superconducting quantum technology process, RF technologies, and radiation detectors, for example, and MEMS sensors. So it's a very versatile clean room. And from quantum technology perspective, especially, it's interesting that we have superconducting technologies and integrated photonics in the same clean room, which enables interesting applications towards quantum photonics and quantum communications, especially. I mentioned already quantum computers that we are building, a bit more about those ones. So we actually started this action for real in 2021 when we initiated this co-development with IQM and between IQM and VTT, and we have had some quite good results and during this development. So already in the year 22 we had a 5-qubit quantum computer launched. Then the next year 20 qubits, and in the next few months we will have a 50-qubit quantum computer. And we, from the very beginning, we have been thinking about combining this with these quantum computers with the supercomputers. So currently it's the 5-qubit quantum computer which is connected to LUMI supercomputer, which is one of the fastest ones in Europe currently. And of course, now then with this hybrid computing, we are also looking heavily on the quantum algorithm and the use of quantum computers, applications for quantum computing side. But today I'm about to concentrate more on the scaling up and the hardware side of things. Just a quick view on VTT's activities on the European landscape. So we are heavily involved in the Horizon Europe, so quantum flagship activities, but also other quantum activities like EuroQCI and EuroHPC in the European landscape. But let's not dwell too long on this one, and let's rather see on the what we actually do on Finland and at VTT on quantum technologies. But just as a reminder that we are a kind of technology and research organization, of course, doing a lot of research, but we do this research heavily also with companies. And here is one reference, public reference that we can mention. Of course, usually we don't talk about anything we do with the customers, even because it's completely confidential. But as an example, that we work with Xanadu on their photonic quantum computers in the photon detectors with them. But the topic of today of the series is scaling up quantum computers, and this is really what we at VTT want to do on the hardware side. So scaling, what does scaling up of the quantum computer, what does that mean? So there's of course many things that you need to scale so that you can actually achieve a large, let's say even a fault tolerant quantum computer in the future. So you will need more qubits, you need to have higher quality of the qubits, you need to have scale up the fabrication processes. You would need to scale up on the system level many things, especially in the superconducting. It's the cabling, which is typically mentioned as one of the issues where scaling is needed, and then of course the number of channels in the successive electronics also. So there's many things that you need to scale up when you are building a really large quantum computer, not with just hundreds of qubits, but we are talking about thousands of or tens of thousands of qubits for really getting some fault tolerance out of these systems. So So what do we then do to solve these problems? So first of all, of course, we are looking into the qubits and developing better quality qubits, and exactly again looking into the fabrication processes. How can we get better quality out of the qubits, so longer coherence times, but also how do we increase the yield and the repeatability of the components that come out of the fabrication processes. Then for large systems, we need to integrate these systems on a chip scale to build complex QPUs, large QPUs, and that integration needs to be also superconducting. Then I have mentioned here single photon detectors. I will show in the following slides how that actually fits very well into the discussion about scaling up. And then I mentioned these QuIC sensors for the reasons that actually QuICs can be used also as part of readout or multiplexing schemes in the cabling side. But maybe for quantum computing applications, either SFQ or then semiconducting cryogenic solutions like cryogenic silicon germanium or CMOS circuits could serve the purpose better. And then on solid state cooling is also something that can reduce the cooling power requirement of the external refrigerator significantly. So all of these things help you to build quantum computers. Let's say scale them up, build them more compact, include a lot more qubits in those systems. Okay, but few examples then for the superconducting qubits, just a kind of reference measurement to demonstrate where we are at VTT. So we have demonstrated a 300 microsecond T1 coherence time from this angle evaporated aluminum Josephson junctions based transmits. So it's a fairly standard process. I would say state of the art result on this one. There's a lot of measurement results from different perspectives on this one. You can see that the quality factors of the resonators are there nearing 10 to the power of 7 to achieve this coherence time. But the angle evaporated qubit process suffers, I would say, overall, not just at VTT, but overall, I would say that the state of the art is still that the repeatability and the yield of the junctions is not very good. And that is not an issue if you make a QPU with maybe tens of qubits, but it starts to be an issue if you do qubit with QPU with hundreds of qubits. You don't get the right frequencies or all the qubits working. But especially it becomes a problem if you want to do more complex circuits, which would include thousands or tens of thousands of junctions. And what are then these kind of circuits? For example, parametric amplifiers, traveling wave parametric amplifiers or tubas, which are typically used for the readout of qubit systems in quantum computers. They require hundreds of thousands of junctions easily for good performance. Or then SFQ logic, for example, which can be also used to drive or control qubits. So that's also one avenue for scaling up the quantum computers to bring some logic, superconducting classical logic, to control the qubits nearby in the cryostat. So for these kind of systems, you need thousands of junctions, and then you need a process which is much more scalable and repeatable. And this is typically a so-called three-layer process or edged process, anyhow, a process of qubit manufacturing where the you don't use liftoff and angle evaporation, but more standard standard etching processes which are closer to the CMOS fabrication methodology. And here we have one of the best results currently. If you see at the qubit frequencies and versus T1 time plot there. So we have a very stable process with high quality for this kind of complex circuits in-house. Then scaling up qubits, quantum computers, you need this 3D integration scheme. Maybe after 20 qubits roughly, this 2.5 dimensional signal routing with the air bridges is not convenient anymore. So you need to take the third dimension into use, and then you need this superconducting through silicon vias and flip chip technology, so that you can build these chip stacks where the qubits and the routing of the control and readout signals are separated on different wafers or chips. And we have this indium-based superconducting flip chip process and the TSP process very well established in our clean room, so we can use this for these complex and large QPU fabrication. Just to give you an kind of view on what it looks like then when we build these more complex systems. This is an example image from SQUIDs, but this is a very similar process that what I mentioned for the other complex structures like SFQs or tubas. So we need a multi-layer metallization systems and then this very repeatable junction process monolithically integrated, and that's what you can see in the first image here. And then the second image shows how we are able to use MEMS manufacturing technologies also for superconducting systems. So here we have this terahertz bolometer, which is based on its kinetic inductance bolometer actually in this picture. So it's a superconducting device which is on this kind of a perforated and suspended membrane. Now I come back to the SNSPDs. So what does single photon detectors have to do with the scaling of quantum computers? So currently one of the bottlenecks of superconducting quantum computers is the amount of RF cables that you need to wire between the room temperature and the cryogenic temperatures where the qubits are. So VTT is working for a concept which you can see on the right hand side there on the upper image, where we would convert these RF signals to optical wavelengths and then use optical fibers to relay these signals, control signals, to the qubit. And that we are able to this way reduce a lot of the number of cables, so we can multiplex several signals in the same fiber, and this then saves a lot of space and also reduces the thermal load by the cables to this cooling system. So this enables then fitting much more signal channels to a refrigerator. And the SNSPD comes in there on the optical to electrical converter on the cryogenic side. So we will use the SNSPDs as the detecting component there on the cryogenic side. And the benefit of this is that the detector itself is superconducting, and it doesn't add thermal noise or shot noise or anything else like a semiconductor photodiode based detector would add to this system. So this is from that perspective also a much better solution than a semiconductor detector there. But of course you can use SNSPDs for many other things too. But this is how we are planning to use this optical integration to scale up the quantum computers. And then as an additional point, you can also see there on the bottom figure that we are thinking about using SFQ, so superconducting classical logic, as let's say a glue logic between the optical electrical converter, so the SNSPD, and then the actual qubit chip, the QPU. Okay, and this brings me back to the point that I already made, that actually integrated photonics and superconductors help a lot in this integration and scaling up quantum computers, not only for superconducting quantum computers, but actually many other optically driven quantum computer platforms could utilize these optical, for example, superconducting detectors, if we have an efficient way of integrating integrated photonics and the superconducting detectors. We have two platforms at VTT for integrated photonics, this 3 micron thick soy platform, and then a silicon nitride platform for visible wavelengths. But this is a nice figure that demonstrates all the capabilities of integrated photonics. So this is very interesting, especially for quantum communications, because this is a very low loss platform. Then there's completely new approaches that are arising in the superconducting field. So typically superconducting circuits are always kind of current or flux driven. Because there's no resistance, you cannot work really with voltage because there's no voltage differences arising. But now with the Josephson field effect transistors, which is a new component devised in the quite recently, this is about to change. So we actually now have a voltage controlled device which can be used in a similar way than a transistor, but for superconductors. So this enables a completely new kind of let's say, logic, for example, and new kind of circuits in the superconducting space. And the applications of this component, let's see what comes out of it, but amplifiers, multipliers, multiplexers, then this logic, there's a lot of possibilities. And what VTT has done on this topic is that we have a very stable fabrication process for these components now, which is quite new development. So now when we again have stabilized fabrication processes, we can really start working on the applications because we know that what we design, we are then able to also fabricate with the good yield. And then I also mentioned these coolers. So here we are really talking about the solid state coolers for instead of this let's say large refrigerators that are used today. And this thinking here is it's actually, one might say that it's a phonon or integrated phonon and electron engineering that we are doing here. It's a similar effect than this CPAC effect in higher temperatures that you are, if you drive current through a device, then you can cool one part of it. But this is separate phenomenon from the CPAC effect, and which works only in the very cold temperatures. But we have been able to now demonstrate that we can go from above 1 Kelvin to millikelvin temperatures with this kind of a cooling device, electrical cooling device. And that maybe doesn't sound like a big achievement. So we are cooling 1 Kelvin by this, but actually the last Kelvin is also the one where most of the power and most of the complexity in the dilution refrigerators lies. So actually, by being able to cool systems from 1 Kelvin with this electrical approach, we only have to have a much smaller external cooler for the same system. So like a dilution refrigerator for millikelvin systems currently is like a room-sized device, but this could actually be a tabletop device. And again, this helps in scaling up the systems when the cooling systems require less space. But this was more or less what I had in mind. Maybe the final reminder is that also semiconductor technologies have a place in this one. So with semiconductor logic and analog circuits, you can do multi-channel things in very compact phase. So especially, for example, in the readout chain after the tuba amplifier, you can do a lot of integration, many channels to a single chip and so forth, to again reduce the space per channel that you need, maybe power consumption per channel, and thus enabling the scaling. So there is a lot of engineering pathways for scaling up quantum computers. So what I'm really want to say here is that a lot of solutions exist, and they are in kind of the problems are engineering problems and not from that perspective physics problems that new physics should be invented. So it's really the hard work of engineering that is now needed for scaling up these quantum computers, and VTT is heavily working on this one, developing new technologies and solutions. And if you are interested in working for us, you can see here what we can offer, and you are always welcome to contact me. And with this one, I will close my speech and thank you for the attention.
So thank you so much, Pekka, for the insightful presentation. It is inspiring to see that VTT is doing this kind of quantum services, and also the leadership that you have in developing these devices, and all around the scaling quantum computing technologies. Next, we will turn our attention to QTest and QPilot, that are two critical initiatives focused on building a robust European infrastructure for quantum device fabrication, testing, and validation. And here I will call to the stage to our next speaker, that is Sarah Puchemal. She's a senior scientist in the quantum photonics team at VTT. She specializes in photonics and optics and plays a vital role in the QTest and QPilot projects. She's responsible for operations, sales, and customer relations, and also for setting up the pilot lines and redefining technical specifications. And her work is instrumental in advancing the European ecosystem for quantum device manufacturing and validation. So, Sarah, over to you. Thank you so much for being here.
Yeah, thank you, David, for the introduction. Good afternoon, everyone. I will talk about QPilot and QTest projects, as David mentioned. So first, a brief motivation on these projects. It started with the CHIPS and CHIPS Act, and as you know, CHIPS have a strategic advantage for Europe and made a significant impact on European R&D landscape and funding. So EU investing heavily on future and emerging technologies such as quantum technologies and semiconductor under Horizon 2020. And electronic components and services, as you see here, the value chain starts from the material and semiconductor equipment for the development and manufacturing of devices and systems. This requires large capital investment in production lines for hardware development and integration. Focusing only on semiconductor parts, semiconductor market value was estimated to be around 500 billion euros in 2023, and it's expected to grow to be almost double in 2030 year. So envisioning this growth, there are huge investment worldwide. For example, Europe is investing 43 billion euros in CHIPS Act, and also following the US investment in chips with 50 billion euros in Science Act, and total business investment up to $150 billion for the US chips manufacturing infrastructure. So this brings me to the point that how important are the manufacturing capabilities and the pilot lines are. And creation and launching of manufacturing pilot lines is the key to establish new processes and equipment and technologies, especially for the new technologies such as quantum. Experimental pilot line, such as QPilot, as you see here, allows for early validation of new concepts to support the manufacturing for quantum hardware industry. And it facilitates the collaboration between industry and RTO across the Europe. So within the seven years of the whole project phases, two phases, first SGA1 and then second SGA2, we would like to develop the European capabilities for the quantum hardware supply chain and validate these kind of operation systems for the offers inside and across the Europe for internal use cases and through open calls for external use cases. So we try to exercise this kind of delivery and service offering points for the European ecosystem in quantum hardware. So the whole project will be 7 years, and it's started in 2023, April. Yeah, here's an overview of the QPilot project. We have 21 partners, and it is a Horizon Europe project launched in April 2023. And we have partners across 9 different countries. And the whole point would be developing and providing access to the first production network for quantum technologies inside Europe. We are a sister project with the QTest. QTest also having 25 partners, and they are developing the testing facilities and providing access to testing infrastructure for quantum technologies across Europe. The total budget for these 2 projects for the first SGA was around 40 million euros. And for QPilot, it's coordinated by VTT. Mika Prunila is the coordinator. And for the QTest, it's coordinated by Gabriele Bulgarini from TNO. And here are the list of the RTOs and service providers and use case companies involved in the project. The joint goal of the QPilot and QTest project is to provide an open access distributed infrastructure for manufacturing, testing, and validation of quantum devices. In a typical product development life cycle of a hardware product, pilot manufacturing is positioned at the last step before the production. We provide through the QPilot, we provide a full cycle of design and fabrication, and then through the QTest, we provide the characterization services for quantum technologies. So we have 4 actions. The main focus of these 2 projects. First, to build a joint European ecosystem for fabrication and testing, focusing on quantum technologies. Second, upgrading the existing infrastructure for piloting and testing, specifically for quantum again. And third, to set up distributed pilot line and testing facility for the European market. And fourth, to validate technologies through single entry point. So what we want to achieve is to establish a capability roadmap for providing experimental pilot line for quantum technologies In mid-run, this capability will be transferred to industrial production lines in the field of quantum computing, quantum communication, and quantum sensing. So we are targeting both fabless customers and customers with the fabrication facilities to provide service for the development of European supply chain, especially startups and SMEs. Operation procedure is through the single entry point and the coordinator facilities for QPilot and QTest projects, which in this case are VTT and TNO, acting as a SEP for this two project. And then, sorry, and then they direct the customers to the right RTOs that matching their services and depending on the request from the customers. So for the QPilot project, we follow a federated approach, categorizing to 4 different technology platforms: superconducting, photonics, semiconducting, and diamond platform. These technology platforms shows the shows 4 different pilot lines with major players across the Europe for that have expertise for each technology platform. Together, they form the whole ecosystem for QPilot manufacturing network. And as it listed under each platform, they are also service providers and the customer companies as an internal use cases for each platform. Here are the technical focus of each platform listed in bullet points. For superconducting platform, we have low-loss superconducting electrodes like niobium and high resistivity silicon. We have low-loss Josephson junctions, aluminum oxide, aluminum junctions, and low-temperature superconducting Philip chip bonding process for Josephson junction circuits. And for photonics platform, we have low-loss soy platform, silicon nitride platform, lithium niobate, an insulator, and we have also active and passive components, and also SNSPDs developed within that platform. And for semiconducting platform, we have multi-level gate stack controlled quantum dots, and also with the different technology, silicon germanium quantum wells, and we have coherent spin manipulation structures provided by the partners. And for diamond platform, we can provide services of diamond growth and fabrication on diamond wafers and different kind of processes, ion implantation and color center creation on diamond wafers. So how do we achieve our goals, and how do we operate to achieve an European ecosystem to address the quantum technology needs? At the beginning of the project, we had the first step trying to gather all the information and input from the use case company and their expectations from the pilot line and RTOs that provide the service. And based on that information, we had the joint meetings between RTOs as a service providers and the internal use case company. So they try to upgrade their recipes and lab fabrication processes to address the needs and demands from the use case companies. And then after establishing a process for the internal use cases, we started the execution phase of the use cases for 2 projects, up to 20 use cases combined. And then in parallel, we worked on developing a process for open call and application to attract more use cases, focusing mostly on external companies that are external to the consortium. We also had few applications from the inside the consortium, and we try to develop a process to and polish the process of service offering through single entry point for these two types of use cases, both internal and external for the projects. And here are our latest results and updates on the internal use cases for the QPilot projects. So we divided them between different platforms. For superconducting platform, and here are the list of companies. List of companies are getting service from the different service providers, and here is the list of the projects and the services they were interested in from the internal use case companies. For photonics also we have 3 use cases for the semiconducting platform, 3 use cases, and 2 use cases for the diamond platform. These all projects, total 12 use case projects, are up and running, and they will be finalized within next few months. In QTest side, we also have 10 internal use cases from different companies. Here are the list of companies that are getting services, and there are some services jointly offered by different RTOs or metrology institutes for the characterization and measurement and the description of the projects. And the same way, within few months, we will finalize the use cases for the QTest project as well. So the second phase, as I mentioned, we also have the open calls for the external use case companies to apply. The reason for the companies to apply to these use cases as an external companies is that we provide the expertise and fabrication facilities to validate their request and the prototype that they are demanding, and it will be a reduced cost, so it's a kind of 100% funded from the project. And also there is a jointly interacting projects running up for these external use cases. So this kind of helps to accelerate the development for the ideas that might be costly for the companies and startups in early phases, but it helps if we kind of do fast validations through QTest and QPilot. Sorry, and most importantly, it will help to build a network and ecosystem to kind of deliver these kind of services. For example, we had some of the services jointly offering by several service providers. So this kind of services facilitates the mutual offering and network offering as inside Europe for the customers. So for the open call processes, we prepared the marketplace, technical marketplace for both projects. And by scanning these QR codes, you could see the latest updates from the technical marketplace. Here's an example of this technical marketplace and service catalog for QPilot project and photonics platform. So there's also description if you click on each one of these services. These are the latest progresses and updates provided by RTOs and service providers for each technology. So you will see the latest updates and the fabrication parameters by clicking each one of these services. And then after choosing the right service, the open call use case companies were in touch with us, and through single entry point, we linked them to the right service provider. And here was the process. We launched the open call text, and now it's closed and selection process is started, and soon negotiation process will begin. So far, by the time that call closed, 17 application submitted. It was 14 SMEs and 3 large-scale companies. And proposal in both projects were ranked by the reviewers. And then roughly 10 use cases will be selected with total budget of 1.5 million for these calls. And here's a country distribution and the platform, technology platform distribution of these open calls. The same goes for the QTest round 1 open call that we had 13 use cases selected in total, and the project will start early next year. And here is also the technology focus distribution and technology platform distribution for the requested services for the characterization and measurements. And the same, we had around 15 applications from SMEs and 2 applications from large-scale companies for the open calls. So those information were for the first round of open calls for both projects. For QPilot, that will be the only run, so we won't have any round 2 for the open calls. But for QTest, we have the second round of the open calls, and here is the instruction and the link to apply for the open calls. And the next cutoff date will be end of March 2025. And by scanning this QR code, you can get you can go to the link to get more information about the second round of the QTest. And it's as I mentioned, it's a good opportunity for especially startups and SMEs to get the services from the experts across the Europe. So what are the next steps for the QPilot and QTest project? So our future orientation and focus will be mostly on sustainability of the offered services. We got a lot of lessons learned from the open call use case projects and the procedures, and also building a collaborative ecosystem and how to build the interoperable ecosystem for the quantum hardware systems across services across the Europe. And we are also interacting with CHIPS Act projects and also giving input to the pilot line proposal projects and the operation model. We give feedback to the how to interact with the open calls and use cases for the existing pilot lines and also future pilot lines. And then we will prepare and plan for the second SGA. And for the second SGA, we would implement the lessons that we learned through the first SGA, and maybe mostly focusing on the more interactive use case and industry and RTO interactions. Yeah. I think that was the last slide. Thanks a lot, and sorry for my voice.
So really insightful, and thank you not only for the presentation, also for being here, even though you doesn't feel you don't feel your best. But it has been really insightful and really good, and I'm shocked that those kind of projects exist to actually help the industry and the quantum landscape. So now we will open the floor for questions. Please use the chat, and I will get also Becca here, so we can have everything here. I haven't seen any questions, so while the people start making questions, I have a couple of them here prepared. So first, a question for Pekka. That is about the quantum computer he has been talking about. So, and super easy question. What are the anticipated use cases for this quantum computer that you have been showcases? What are the plans to launch it, and how will it position Finland in the global quantum landscape?
Thank you, David. Excellent questions. So for the use cases, up to this 50 qubits quantum computer, there is not a kind of maybe a real quantum advantage to be expected from this size of a quantum computer yet. But the applications that we are especially looking in are in molecular simulations and material modeling. And that's where there has been actually recently quite a lot of interesting results from many different groups in worldwide, even with around 50 qubits, but maybe even more in the range of 50 to 100 qubit quantum computers. But I think those applications are a big kind of focus area for us. The other field is then different kind of optimization problems and looking into the use of or quantum AI, using quantum computers for AI too. But that's still, I think, farther away on the application side. Well, that's about the applications, and then about how we are about to launch the 50 qubit quantum computer. So we're looking into launching it in the next about the next 3 months. So the development is in progressing well and in I would say the end phases. So that's roughly the timeline currently, and then we plan to launch it in this kind of a cloud service. So everybody interested can then contact us and get the access to that computer. Similarly, then you can get access to the other cloud-based computing services that there are available. Then about the position in the landscape, I would say that there's not many 50 qubit quantum computers in the Europe yet. So definitely that gives us a very prominent position within Europe. And especially on the superconducting side, I don't think that there is a single quantum computer with 50 qubits in Europe yet. Of course, globally, if you compare, for example, for IBM, which has several quantum computers above 100 qubits, then of course there's not it's not as big as that one. But then also comparing just the qubit numbers, you also have to, of course, compare the connectivity of the qubits and quality and so forth. So it's not just that straightforward that the more qubits you have, the better it is. But I would say that definitely we see that we are in a good position in Europe, but globally we still need to continue to get to the global forefront, and that's exactly what we are doing. So we are not stopping the development to the 50 qubits, but going towards 300 qubits next. We have the funding to go roughly for next 3 years then towards this next step.
Yeah, and actually that's a really good point you raised, that maybe it would be like for another QWave, like that the comparison about different technologies and even computers is not so straightforward. It's not like saying I have a bigger number of qubits and that's why I'm better. That's not really the case. And you raised the point about the connectivity between the qubits, that I believe that it's really important. And people, like maybe people that are not so technical don't realize these kind of things. And I think that could be a really good topic for another QWave series, like comparison between quantum computers and also benchmarking. That is a topic that is really relevant. I have here a question from Edmundo Sanchez that is for the QPilot. If there is any intellectual property coming out, are the general rules about who has claim to it, or for any background IP use in particular, as there any industry partners?
Yes, thanks. That's a good question. And yes, we do. There's established rules for IP management in QPilot project and proposal as well. And like in general, IP stays with the party who develops the IP. And also for the external use case company, we have the procedure in place, and also they can be negotiated one by one through with service provider and then the use case company.
Thank you. I don't see any other questions, and we are almost at the time. So I will ask just a last question for you both. Maybe you can start, Sarah. That I will ask about what are like the main task or the main stoppers about the scaling quantum computers. I believe that Sarah will be more about how QPilots can help in the scaling, and for you, Pekka, what are the things that you have seen that is the more like difficult to address or the more impactful in other way?
From QPilot point of view, so I think it's mostly the fabrication and the nanostructures and microstructures fabrication yields for the superconducting, semiconducting, and photonics platforms, and that's our main focus in QPilot, to address those challenges and provide the kind of experimental and somehow established fabrication process for the key elements for the quantum computing. That's our approach for QPilot. So maybe Pekka can comment in general.
I would actually also emphasize the fabrication, because the scaling, there's a lot of things that you need to scale as discussed, and there's different kind of applications for that one. But finally, it's about the quality of the qubits and the repeatability of the fabrication, so that you are able to really make large QPUs with hundreds or even thousands of qubits. So I would really say emphasize that the stability of the fabrication is very critical for the scaling.
Thank you. So one last question that I see in the chat, and then we can close the session. So Anna asks, could you extend or the quantum algorithms that your system leverages?
Well, maybe I'll take that one, or at least start. So as I mentioned, we are looking into the material modeling and molecular simulations especially. So there are many different models, but and ways how we are looking into it. But very many of these, let's say, kind of energy calculations, this ground state energy calculations, they use some variational approaches, and this is where we see the benefit of using HPC computer tightly connected to the quantum computer. So this is kind of the approach what we are taking, and looking into different kind of material models and then problems here. And we are currently kind of evaluating where we get the best results. So unfortunately, I cannot give you a kind of explicit and simple answer with just a single model or an algorithm.
So thank you so much for your talk and the insightful session. I want to thank first our speakers, Pekka and Sarah, for sharing their expertise and for providing such a valuable insights about what's happening in VTT and also through the QPilot and QTest projects. Also to our audience, thank you for your engagement, for your questions, and for your time. Your participation is what makes this session impactful. And I will just close by saying that stay tuned in our different platforms, in our website, in our LinkedIn, in our newsletter. Here you have all the websites and the QR for easy access. And also, if you are a member and you want to be in one of these QuIC sessions, just talk to us, send a mail. And if you want to propose a topic, also is welcome. And if you are not a member and you want to become one, please also contact us. Thank you all. Thank you, Sarah. Thank you, Pekka. And thanks to the people who is on the other side of the streaming. Bye.
Thank you.
Bye.